How do the seesaw's riders affect one another? The answer to that question is that they support one another and they exchange energy as the seesaw rotates back and forth. Let's start with the support issue. And to do this, I'm going to treat the seesaw as a facilitator rather than the object of our main attention. I'm going to define the center of rotation as lying in the middle of the pivot. So the axis of rotation for this entire story is right here at the pivot of the seesaw. But otherwise, the seesaw is just helping the red rider exert a torque on the purple rider about the pivot, and the purple rider exert a torque on the red rider about the pivot. Well, you might wonder why the red rider should ever care about exerting a torque on the purple rider. That's because the purple rider is already experiencing a second torque, a torque due to gravity. Gravity is pulling downward on that purple rider at a lever arm from the pivot, the axis of rotation. So gravity by itself is exerting a torque on the purple rider, and that torque is toward me. That is away from you. To keep that purple rider from undergoing angular acceleration and plummeting toward the ground, the red rider comes to the rescue. Okay? The red rider is exerting a second torque on the purple rider, and that torque is toward you. So the second torque acting on the purple rider cancels gravity's torque on the purple rider. This is all about that pivot, and prevents the purple rider from undergoing angular acceleration. Aha! The red rider really is supporting the purple rider. How about the other way around? Well, the red rider is also experiencing a gravitational torque. Force is down, lever arm is toward your left, so the gravitational torque on the red rider is toward you. By itself, that would cause the poor red rider to undergo angular acceleration, boom, and drop toward the ground. But once again, the purple rider comes to the rescue. And now the purple rider is exerting a torque on the red rider that is this way toward me. Ha! It cancels the gravitational torque on the red rider and saves the red rider. So, the long and short of it is, the red rider is keeping gravity from twisting the poor purple rider to the ground. And the purple rider is stopping gravity from twisting the poor red rider to the ground. They really are supporting one another. So we have two torques between the riders. The red rider is exerting a torque on the purple rider, and the purple rider is exerting a torque on the red rider. How do those two torques compare? They turn out to be exactly equal in amount, but opposite in direction. That's an example of Newton's third law of rotational motion, which observes that for every torque one object exerts on a second object, the second object exerts an equal but oppositely directed torque back on the first object. That's how our universe works again. It's never violated, it's always there. So the red rider, when it exerts a torque on the purple rider, causes the purple rider to exert an equal but oppositely directed torque back on the red rider every time. And that ultimately allows this whole thing to balance smoothly. At the same time, the purple rider rescues the red rider from the grips of gravity. The red rider rescues the purple rider from the same clutches. And so the two objects here both reach the balance condition at the same time. They all end up with no overall torque due to gravity. This mutual support idea still works when one of the riders weighs far more than the other. If I replace the red rider with this silver one, I can't put that heavy silver rider all the way at the end of the board. I have to come in close to balance the seesaw. It's right about here. And look what has happened. That rider weighs far more than the red rider did. So if I put it out far, it would produce way too much torque to support the purple rider. It would turn the purple rider into an astronaut. So, by pulling the silver rider in closer to the pivot, I have compensated for the silver rider's greater weight by shrinking the lever arm that the silver rider uses to produce a torque about the pivot. As a result, the silver rider is still just perfectly supporting the purple rider against the purple rider's gravitational torque. So, that part of the balance still works. How about the purple rider's support of the silver rider? Well, it still works there too. The gravitational torque acting on this silver rider was reduced by bringing the silver rider in close to the pivot. Gravity is pulling down with a big force on that heavy silver rider, but since that force has only a short lever arm with which to work, it doesn't produce all that much torque on the silver rider about the pivot. As a result, the purple rider is still able to support the silver rider. The silver rider may be heavier, but because the silver rider is closer to the pivot, it doesn't take as much torque to support the silver rider against the torque produced by gravity itself. I haven't talked much about units in rotational motion because they're somewhat complicated and they'll distract us from more important issues. But let me take a moment to mention the units of torque. In the SI or metric system, the unit of torque is the Newton meter, and it corresponds to a force of 1 Newton exerted at a lever arm of 1 meter from the center of rotation. In the English system of units, the unit of torque is the foot-pound. It corresponds to a pound force exerted 1 foot from the center of rotation. I introduced the units of torque in part so that I can ask a question. Here is a wood screw, and I will screw it into the wood by exerting a torque on it using my right hand that is down toward the wood. And now I will unscrew the screw by exerting a torque on it that is up, out of the wood. If in both cases, inward torque and outward torque, I exert a torque in the amount of 1 Newton meter, what torque does the wood screw exert back on me? If I exert a torque of 1 Newton meter on the wood screw, it has to exert a torque of 1 Newton meter back on me in the opposite direction. That's Newton's third law of rotational motion. So as I exert a torque of 1 Newton meter downward into the wood block, it exerts a torque of 1 Newton meter up, out of the wood block, on me. And if I exert a torque of 1 Newton meter out of the block, upward, on the wood screw, it exerts a torque of 1 Newton meter downward on me. Every time. Now let's watch the riders exchange energy as the seesaw rotates. I've pretty well balanced the board here. I have the red and purple riders at about the right distances from the pivot so that the seesaw balances. It experiences zero net torque and therefore rotates at constant angular velocity. I'm going to hold the riders in place so that as the seesaw rotates, they don't slide about and possibly fall to the floor. But what I want you to do is watch the altitudes of the two riders. I'm going to make the seesaw rotate at constant angular velocity toward you, that is like this, and the red rider descends as the purple rider rises. That means the red rider's gravitational potential energy is decreasing, while the purple rider's gravitational potential energy is increasing. Where did the energy from the red rider go, and what provided the energy to the purple rider? What a mystery. I wonder. As you might suspect, the red rider is transferring energy to the purple rider by way of the seesaw. There are a number of ways of following that energy transfer, so I'm going to pick what I think is the most straightforward path. It involves the work that the red rider does on the seesaw and the work the seesaw does on the purple rider. I'm going to make the seesaw rotate very slowly at constant angular velocity toward you. And as I do, I'll tell you how the transfer is occurring. Let me get it started here. Okay, it started, we're going very slowly so I have time to talk. The red rider is pushing down on the seesaw as the seesaw moves down in the direction of that downward force. So the red rider is doing work on the seesaw. At the same time, the seesaw is pushing up on the purple rider, and the purple rider is moving up in the direction of that upward force. So the seesaw is doing work on the purple rider. The job is complete. The red rider is transferring energy away to the seesaw, and the seesaw is transferring energy away to the purple rider. Hope you can follow that. So, energy is flowing through the seesaw from the red rider to the purple rider. Pretty neat. As the rotation occurs in the opposite direction, so I'm going to make it rotate at constant angular velocity toward me. In this case, the purple rider is pushing down on the board as the board moves in the direction of that push. Therefore, the purple rider is doing work on the seesaw. The seesaw is pushing up on the red rider as the red rider moves up in the direction of the seesaw's push. So, the seesaw is doing work on the red rider. Again, energy is going from the purple rider into the board and from the board into the red rider. Because the seesaw is balanced, all of the gravitational potential energy lost by the rider that's moving downward becomes gravitational potential energy in the rider that's moving upward. The transfer of gravitational potential energy to gravitational potential energy is perfect. If the seesaw isn't balanced, well, then it undergoes various types of accelerations, and kinetic energy becomes part of the equation. But this arrangement, where a balanced seesaw is transferring energy, and particularly gravitational potential energy, from the descending rider to the rising rider, works even if the riders have different weights. If I replace the red rider with the much heavier silver rider and balance the seesaw again, I achieve that balance by putting the heavier silver rider close to the pivot. Now, it's pretty well balanced. As the seesaw rotates at constant angular velocity, which is what it normally does, the silver rider, who is close to the pivot, doesn't move up or down very much anymore. Right? They're close to the pivot. They only move up and down, this far, as the purple rider is moving up and down, much farther, more than a hand width. Ooh, that is the secret, or maybe the explanation behind the perfect transfers of energy again. If I again rotate this balanced seesaw at constant angular velocity toward you, the silver rider is descending. It's pushing down on the seesaw board with a large force because it weighs a lot, but that seesaw that it's touching isn't moving very far. A little bit, but not all that far. So it's doing work of a reasonable amount on the seesaw. At the same time, the seesaw is pushing up on the purple rider with a more gentle force, but the purple rider is moving a longer distance. So the work the seesaw is doing on the purple rider is the same as the work the silver rider is doing on the seesaw. Just make sure that's clear again. The silver rider is exerting a large downward force on the seesaw as the seesaw is descending a short distance. At the same time, the seesaw is exerting a small upward force on the purple rider as the purple rider moves upward a large distance. The product of force times distance traveled in the direction of that force, the products are the same. The work done by the descending silver rider on the seesaw is the same as the work done by the seesaw on the rising purple rider. Energy is transferred perfectly. This arrangement of the seesaw, where a heavy rider can lift a light rider or a light rider can lift a heavy rider, highlights the fact that the seesaw is an example of a lever, one of the simple machines. Like all simple machines, the lever allows you to change the amount and/or direction of the force you're using to perform a particular task. To make that clearer, in this case, let me get rid of one of the riders. Purple rider, take a rest. And now I'm going to lift the heavy rider with my hand by exerting a force directly on the seesaw. I can lift the heavy rider. And in this case, the force that I'm exerting on this side of the seesaw is relatively small, much less in amount than the weight of the heavy rider. But as I lift the heavy rider, I have to move the seesaw I'm pushing on much farther than the seesaw moves the heavy rider. So I'm doing work as I push down on my side of the seesaw. And I'm doing it by exerting a small force over a large distance. Whereas the seesaw is doing work on the heavy rider consisting of a large upward force exerted as the heavy rider moves a short distance. So the work I do on the seesaw is the same as the work the seesaw does on the heavy rider, but the relationship of force and distance has changed. And that's typical of many levers in our world. Which brings me again to a question. Let me get out a familiar lever and ask you about it. It's an all too familiar situation. You take a nail, you pound it into a piece of wood, and then you change your mind and you want to take the nail back out. So you grab the nail with your hand, you pull as hard as you can. No luck. Can't get that nail out. What are you going to do? You take a claw hammer, that is a hammer that has a groove in it meant for grabbing the heads of nails. And you grab the head of the nail with that groove, tip the hammer, and it plucks the nail right out of the wood. So the question is this: what aspect of what I did to the hammer is the same as what the hammer did to the nail? The hammer acts as a lever, and the work I did on my part of the hammer was the same as the work the claw did on the nail, as the whole system rotated about an effective pivot where the top of the hammer touched the wood. So I was doing my work with a small force exerted over a long distance, as the claw was doing its work with a large force exerted over a small distance. This is why I was able to pull out the nail. It was stuck tight, and it needed a huge force to pluck it out of the wood. I couldn't provide that big force with my own hands directly, but with the help of the hammer, I could pull it off because I have mechanical advantage associated with this lever. I'm moving the lever far from the pivot so I can use a gentle force, and it's moving the nail close to the pivot, so it provides a huge force. I don't get something for nothing, though. I have to exert my force over a long distance, whereas the claw exerts its force over a short distance. Nonetheless, the mechanical advantage provided by this lever allowed me to do something I couldn't normally do, namely pull a nail out of a piece of wood. As you can see, the riders' interaction on the seesaw is pretty sophisticated. Not only are they supporting one another, but they're exchanging energy as the seesaw tips back and forth. The seesaw is just a kid's toy, and yet it exhibits all this really amazing rotational behavior, and in particular, it acts as a lever, allowing one rider to lift the other rider, allowing a heavy rider to lift a light rider, and a light rider to lift a heavy rider. Wow, pretty much something for everybody.